11. I'm in Section M03, Spring 2013. This is Lab 5, Part 1, At-Home Video Lab Report, Motion of Falling Objects. The objective was to model and analyze the motion of a slow and fast falling object from rest, and then relate each of them to Newton's second law, taking into account all forces acting on the objects. What we learned was that objects dropped from rest will experience a gravitational and a drag force, and that as an object's velocity increases, so does the drag force on the object until it becomes equal and opposite of the gravitational force, and the net force becomes zero, and the object reaches terminal velocity, doesn't accelerate anymore. For my video, I used a ping pong ball for my slow falling object and a tennis ball for my fast falling object. I used a calibration stick to to measure something really close in the background, a door hinge, and then I put my axis right here, made it start at 0 just so that I get a nice starting point, and then I clicked the center of the ball at each point, and you can see that the frame rate was a little bit slow, so like I clicked the farthest part of the ball because I mean obviously it has to be there if that's showing up on the camera. I then used this data on the right I put it in Excel, and I made a graph of, obviously this is the experiment, and then I used Python to make a model of what should have happened according to Python. These are the formulas I used. Force of gravity is just negative mg on the y component, mass times gravity, 9.8. And then force of drag is negative a constant b, which is different for every object, and then an object's velocity vector. You'll see that in Python. And then the net force is just the force of drag plus the force of gravity. But for this part, we didn't actually use that just yet. Ball's mass, found that, put in the force of gravity vector. Then for this part, F net is equal to force grav. And I ran that, and for the slow falling object, right here in the green is the tracker data, and then the blue crosses is the data from Python without drag. And you can see it doesn't match up because there obviously is drag. That's a real world thing, and the model doesn't show that, so the velocity increases a little bit too fast. So then I went and changed the program, uncommented this, made this plus force drag, and then I made the arrow for it. It's not showing up for some reason when I run it, but ran that and got the line in yellow, which perfectly mapped what actually happened in the experiment. And B was, I think, 0.0007. That might have been the wrong Python thing, but then the same exact thing for this fast falling object. The green is no drag, and the tracker data, oops, I labeled them wrong, but this is the program with no drag. The blue crosses are tracker, and then I did Python with drag, modeled it perfectly. So what does it mean? With the drag of the object reaching terminal velocity and the slope of the line at 0, this happens when you use force of drag and net force, and force of drag continues to increase until it's equal and opposite to the force of gravity. And you see the slope here is 0, so acceleration is at 0. This is a graph of the velocity without drag, with drag. You see this is terminal velocity. I used a bigger time step just because mine was too small for it to actually show up. What if we started with the velocity? I did that and just made it like -10 on the velocity vector initial, and the object still does not reach terminal velocity because the window of time is so small. You see it right here with drag, it reaches 12.75, but over here it should be around like 20. That was just because the time step was too small. Thanks.